So the periodic table is a map. It's like a map. Knowing how to read the map, it will give you a lot of information that is useful. I can probably teach 90% of the class by just looking at the periodic table because I can predict properties, I can predict behavior, I can predict how things are gonna combine with each other. I can do a lot with this periodic table. If you know how to use it, it will help you understand a lot of things. So it's like a grid. It's a grid that made of groups or families and periods or rows. So your groups are your columns. They go from 1 to 18 if you use that notation because you have 18 columns. But there's a different way of naming those columns, which is used, and if you understand it, it will make things easier. And it's that some of those columns will be labeled A, and some of those columns will be labeled B. The ones labeled with an A are considered representative elements because those are the ones that interact with each other the most of the time. The B's are your transition metals. They're more heavy elements. A lot of them are radioactive. Now, if you notice, the periodic table have 2 rows at the bottom. Those are your inner transition metals. They go after the 6, 7 column. There's a spot where they go in there. The only reason they're pulled out at the bottom of the page is so all those elements can fit in one 8 by 11 page. There's no scientific reasoning on why they are at the bottom, just to make it convenient for them to fit in a piece of paper. That's the whole reason. So you have 18 columns. Those are your families or your groups. And you have your periods, your rows. Your rows, there's only 7 of them. Right now, if you look at the periodic table that we have on the wall, all the spots are filled, meaning there's no spot to put any more elements. Those are all the elements that have been discovered so far. The Chinese claim that they have about 7 or 8 more new elements, which, if proven that is correct, will mean we'll have to add a new row into the periodic table because we'll need to make them fit somewhere. That will not happen until those claims can be verified and those experiments repeated. Right now, that's on the works. There's also talks out that they're going to change the look of the periodic table. I don't see that happening anytime soon. But there's a lot of work around how to make the periodic table easier to understand and show properties and behaviors. For now, we'll use it the way it is. So if we look at the periodic table, we have 3 major groups. They're divided by this big black line that you see in it. In that periodic table is red. Anything from that line to the right is what we call the metals, including the 2 rows at the bottom. Anything to the left are the metals. Anything to the right are your non-metals. There's more metals than non-metals. The metals tend to be solid, conductive, shiny. We have more metals than we have non-metals because non-metals tend to be brittle, solid, or gases. Metals conduct electricity and heat. Non-metals do not. But being less elements, they react the most and they're involved in a lot of organic situations, especially in the body, human body. So 3 major groups, they're divided by that staircase: left metals, right metalloids, and then we have a handful of them, which in this slide are in blue. We call those metalloids. Those are your semiconductors. They're used in the semiconductor industry. You can find it in your phone, things of that nature, because they behave like metals or non-metals, depending on the situation, so have properties of both. So metals, metalloids, and non-metals. You need to be able to recognize which one is which by just looking at the position in the periodic table. So if I tell you potassium is a metal because it's on the left side of the periodic table. And bromine is a non-metal because it's on the right side. And then silicon is a metalloid because it's touching that staircase line, and so on. So those are easy questions. But let's look at hydrogen. Hydrogen, you will think it's a metal because it's on the left side of the periodic table. But hydrogen is conflicted because hydrogen only has one electron. Having one electron and one proton, it doesn't want to get rid of that electron. So what it does, instead of losing the electron, it likes to share the electron. Sharing of electrons is a non-metal behavior. So hydrogen, even though it's in the metal side, is considered a non-metal because of the way it behaves. There's very limited situations in which hydrogen will lose that electron. We are not going to look at those situations. So for this class, hydrogen is a non-metal. There's some family groups. Well, you know the columns are your families. Some of those groups, they all have names, but some of them you do have to remember. For example, group 1, those are your alkali metals, and group 2 is your alkaline earth metal. The alkali metals are never found pure in nature because they are super reactive. The alkaline earth metals are less aggressive than the alkali metals, but they're still very reactive. You do not have to memorize them, even though it says here memorize this for essential for navigating the map. You don't have to memorize them because you can use that periodic table, just be able to recognize them. If I mention out of this list which one is an alkali metal, you should be able to recognize which one it is by just looking at the elements in that column. So make sure you remember this name. So group 1 is alkali, group 2 is alkaline earth. There's a couple more. On the other side, we have the last column, which are your noble gases. And there's a reason why they are in the last column. We'll look at that next week. And then we have the halogens. Like the alkali and alkaline earth, the halogens are extremely reactive. Noble gases are considered the royalty, means they don't want to mingle with anybody. They don't like to react with anybody. And as we move on in the class, you'll see why is that. We don't have enough information to prove why noble gases don't like to react with anybody else. So 2 groups on the left side that you need to know, 2 groups on the right side you need to know. Let me see what's coming here. And the last 2 groups are everything in the middle is called transition metals, and everything at the bottom are inner transition metals. They're all transition metals. They're called inner transition metals because they're embedded right here. right after barium and radium. All the inner transition metals are radioactive. If it is radioactive, it means most likely it is being created in a lab, and only some of them can be found in nature, like uranium. And there's other ones that can be found as traces, but a lot of them are just made in the lab, especially those with a high number, with a high atomic number. Okay, so this is the time for a little story. Mercury. In the 1700s, doctors used to give mercury to patients, and they did that to help cure diseases. But mercury will often die because mercury is a heavy metal, it's very toxic. So you cannot just drink mercury and survive. You will die. That's not the kicker. Mercury is not quite found in nature that easily. So how will they find the mercury? Well, they will give mercury to a patient. They will wait for that patient to poop. They will grab the poop, take the mercury out of the poop, and here it goes the next patient. So eating shit takes a new meaning. I'm not making this up. It is very true. They didn't know any better. They will clean it the best they could. But you will be eating poop from the other patient. That way, that's what makes chemistry so much fun in all these stories. Another story, this one is not as bad, is Roman times. Roman soldiers will use bromine bombs. So they will throw bromine to their enemies. That will create a gas. The gas will kill the enemies because bromine gas is very toxic. They didn't understand the theory. They just knew if I throw this thing at my enemies, they will die. That's all they knew. That's all they care. So chemistry has a place in history. It's been used throughout a lot of it. And you can find examples all throughout the history of the world. Now, okay, I have a couple of things, but all these stories come out of this book. It's called The Disappearing Spoon. I'm not going to make you buy it or read it, but if you are someone that likes reading and like reading unique things, this is a great book to read. That story about the mercury is right on chapter number 2. And then there's other, as you move on through the book, there's other stories. There's a lot of funny things in there. But let's go back because I saw that I have a few things I had to go over. So this thing called mapping the charges, we are going to leave for next week when we do naming. So I'm not going to make you worry about it right now. Just remember, metals get attracted by non-metals because the metals tend to be have positive charges. The non-metals tend to have negative charges. And that's the basis of combining elements together. That's the basis of naming that we are going to do next week. So we'll talk more about this next week. One thing that I want you to remember, and you are going to have to memorize this. The periodic table has 7 elements, and they're hydrogen, nitrogen, oxygen, fluor, chlorine, bromine, iodine. When you go in nature, you just don't find an atom of any of those 7 by itself. You find it combined with itself. So you always find H2 or N2 or O2, F2, Cl2, Br2, I2. Those are the only elements that when you go in nature, they're found combined with each other. There's a reason for that we'll deal with a little bit later on. But for now, just know there's 7 elements that are considered diatomic, meaning 2, because it's combined with itself. You have to remember those 7 when we get to chemical reactions. You need to know that when we start writing those reactions, you write it as H2, you just don't write it as H. There's no such thing. Again, they're not found alone in nature. They always travel in pairs. So summarizing, when you look at the periodic table, you have the letter, which is your symbol. Some symbols have 1 letter, some symbol has 2 letters. If it is 1 letter, it's always an uppercase letter. If it is 2 letters, the first one is uppercase, the other one is lowercase. That's how you recognize the elements, by the symbols. They all have atomic numbers. They all have atomic masses in the periodic table. Some periodic tables have more information than others. Sometimes they add the charges or oxidation states, or they add this thing down here. Those are electronic configurations. We are going to deal with those later on. Next week, we'll deal with the charges towards April. We'll deal with electronic configurations. That's done towards the end. Okay, so that's pretty much everything you need to know about the periodic table. It's not everything you need to know. There's a whole lot more. But for now, to be able to understand what's coming, that's all you need. Please make sure you don't forget to bring your periodic table next class.